Hello, this is Jack Jackson. In this video, we're going to be talking a little bit about the fundamental theorem of calculus. The fundamental theorem of calculus, as its name might suggest, is very important or fundamental to the study of calculus. In calculus, we study two main branches of calculus, that is the differential calculus and integral calculus, based on the concept of the derivative and the definite integral for the two parts. Both of those take pre-calculus concepts and then apply a limit to them. In the case of the derivative, we're taking the idea of a slope. Slope of a secant line, we apply a limit process to that, we get the slope of a tangent line or instantaneous rate of change, which is the derivative. In the case of the definite integral, we are looking at areas basically. So we're taking area under a curve, breaking that up into, making an interval in the domain up into subintervals, forming rectangles above that, summing the areas of those rectangles, then taking the limit as we get more and more of those rectangles of smaller and smaller widths. Now, you might look at that and think, well, those things don't really have that much to do with each other. Maybe they're completely independent concepts. But in fact, they actually have quite a bit to do with each other, and that's what we're going to start to see in this video. The fundamental theorem of calculus has two parts. This is what's normally known as the second part, which I think we should actually talk about first. So this is sometimes called the second fundamental theorem of calculus, and it's kind of show you how it works. So with this app that I've made in GeoGebra, and by the way, this is available through the GeoGebra website. So with this app, we can type in a formula for a function. So here I have f of x equals 4 minus x squared divided by 16. Type any formula you want in there, and you'll see it graphed in this left window in red. So we're going to have two windows here. If you open this in the app, you'll be able to see the two windows there, and you can adjust them. Now, what we're going to do is we're going to integrate this function, okay? But we're going to integrate it from a up to this x value. So to start out with, just set all of these to 0. And so let's look at what happens over here in this picture as we slide this to the right. As we slide to the right, notice that we're accumulating area. And this area function, if we integrate from here to here, we're getting that area. So right now it's 8.95. And we can take this and we slide and we accumulate more area. Now areas above the x-axis when we integrate left to right are positive, and they add to the integral. Now once we get over in this area here, now we're starting to get areas that are below the x-axis, and they subtract from the integral. So we have what we would call an accumulation function that is adding these up. So it's basically taking this green area minus this red area. So we're taking a function here. I changed the letter here so there's not a confusion here. Hopefully the t can be thought of as just your function input variable for this function here. But we're going to integrate it up from an a constant a, to a variable x. This creates a function of x. And I'm going to add to that some constant. Right now we're just going to let that constant be 0. And this gives us an accumulation function or area function. Okay, if that constant is 0, then it is this green area minus that red area. And so we can see that one way we can think of an integral is by accumulating things as we go across. Now, let me also just point out something about this. This area here is going to be added to the integral. This is going to be subtracted. So at some point here, there's some point in here, I don't know if I can get it exactly, but there's some point where somewhere between there and there, where the red and the green areas balance, and we're back at 0. And as we go further to the right, we're accumulating more negative area, or negative signed area, than we are positive, and so the integral becomes further and further into the negatives. But, and of course, the reason for that is when you're doing your Riemann sums that this thing is based on, we have a positive width because the width is, say b minus a, or in this case x minus a, and divide by n. That's a positive number because x, or B is to the right of A. But then the heights are positive here, and the heights are negative here. I probably shouldn't say heights, because heights are always positive. The value of the function is positive here, and the value of the function is negative here. And so when we get our signed areas, these are positive and these are negative. And that's illustrated by what we see here. I think I could also drag it by just moving this point, or by moving the slider, or by typing in a number here. I can kind of get whatever I want. So if I want to go to 10 here exactly, I can just type 10 in there. It'll go directly there. I could slide with the slider here, or I could actually slide this point as well. So I have some options there. Now look what happens when you go the other direction. Now the y values are positive when we do our Riemann sums, but the delta x's are negative, because when you do b minus a or x minus a, it's a negative number. So this time, areas above the axis are subtracting from the integral, and areas below the x-axis and above the curve are adding to the integral. So when you're integrating right to left, areas above are positive, areas below are negative in what they contribute or accumulate to the integral. When you're integrating left to right, right to left, it's exactly backwards. Areas above subtract from the integral, areas below add to the integral. So either way you go, the integral is the value of the green part minus the red part, the way I've got it shaded in this application. Okay, so that's that. So the thing I want to show you, though, is this actually generates a new function. So no matter what x is here, which we're thinking of x now as being a variable amount, which it can go either direction, and this one it could be in any real number, it works, then that is going to give us a point that we can graph here in the right window on the accumulation function, this function a of x. So this just gives us a way to generate a new function. So now you notice as I move this around, we get different amounts. So we're accumulating more and more area here, so notice that that function is going up. We start here at 0, it's going to start at the origin, start at A, which is 0. And since C is 0, this starts at the origin. And as I go further and further right, we're accumulating more and more area. So notice that point is going up, going up, going up, going up, going up. What happens right here? Well, let's see. That's what it'll be. It's going to be where it's going to start accumulating negative. So now it's going to start going down. So that's going to be the maximum point on this function. And then it starts back down. Some point we're back where we started. It hits the x-axis, and now we got more negative than positive, and so it goes further down. If we go the other direction, remember this is going to be negative values, so this goes down. More and more negatives, further and further down. It's a minimum right there, and comes back up. So whatever this function is, it's going to hit a minimum or a maximum whenever the original function over here on the left is at the x-axis. Now, I can actually graph that function right there, and we can see that going on. So that has a function there. And so this is what we call an accumulation function. So the first thing we notice is if we take a function and then we integrate it, say take a function of t, integrate it from some constant up to x, that generates a new function. Okay, an accumulation function. So this gives us a way to take existing functions and define some new functions. In fact, there are some very important functions that this is exactly the way they are defined, and there's no way to write down a nice formula for them. The most famous of these is the normal probability distribution from probability and statistics. That distribution is actually defined in this way. It's an accumulation function of some normal, what we call the normal probability density function, which is over here, the PDF, and the normal CDF, cumulative, accumulation function. The cumulative density function would be over here for the normal. If I've typed in the appropriate formula here, that would define a formula here. Okay, I'm going to stay with this one for a while though and continue. Okay, so you can see that function graphed out. Now, notice some things that happen. Again, the maximum on this curve happens when this is at a 0, and again when this is at a 0 here, we get a minimum on this curve here. So that's some interesting things. The maximum right here on this curve is where we got the inflection point over here on this curve. Now, do some of those things start to sound familiar to you? What happens if we do this? What happens if we take a function, we integrate it up to x, but then we turn around and take the derivative of that? So over here I'm going to graph the derivative of this accumulation function, and look at that. Does that look familiar? Well, I don't necessarily have the scales on these exactly the same, but if I did, we would see that that these are exactly the same function. Let's see if I can zoom in towards. That's close. That's close to the same scale there, and you can see these are the same function. Okay, so that's an interesting conclusion that we can reach, and the conclusion is, well, let's do this thing here. If we move this c, then we are just giving a vertical shift of this function. Okay, so let me go back to c is 0 for a second. So what we're saying here is that this blue function is an antiderivative of the original function f over here. In other words, if you take the derivative of the blue function, the accumulation function, you get the original function here. Okay, and we take the so that means the blue function is what we call an antiderivative of the original function over here on this side. So this is the idea of an antiderivative. Now, if we shift this blue function, we get all other possible antiderivatives. Now, as you know, adding a constant to a function does not change the value of the derivative. The slope at this point right here where I am is the same no matter what I do as far as a vertical shift. So the derivative is going to be the same. The derivative of constant's 0. And if we take the derivative of this thing here, the derivative of this c part's going to be 0 anyway, so that's irrelevant. We just get different antiderivatives. So now you can see all the entire family of antiderivatives. Okay? If we change the value of a, that also turns out, as you see, to give us just vertical shifts. So for different values of a and different values of c, we can get different antiderivatives, but this idea gives us a different derivative. So this is the second fundamental theorem of calculus. A lot of times you'll see it without the c written here. But if we take a function, we integrate from a constant to the x variable, and then then we'll get a function of x, an accumulation function. If we take the derivative of that with respect to x, we're right back at our original function, this time evaluated not at t, but at x. So the derivative of that accumulation function is the original function that we started with. So in this sense, derivatives and definite integrals are in some way inverses or opposites of each other. So if we use a derivative, an integral, to define an accumulation function, and then we turn around and take the derivative of that accumulation function, then we're right back at the original thing. So two big things that you should get out of this. Number one, we can form new functions from existing functions by integrating them, and that process produces a new accumulation function. And so definite integrals are the language of accumulation, and so they can be used to measure accumulation in real-world examples, right? So in application problems. And then also, in some sense, the derivative and the integral are opposites of each other. We're going to bring that part home as we go on to our next video, where we talk about the first fundamental theorem of calculus, which also tells us something about this. But basically what we're going to do is we're going to reverse the order. Instead of integrating first, then doing a derivative, we're going to try it the other way around. Do a derivative and then an integral. So come back for that one in a little bit.